Here I have a set of ordered pairs that I would like to represent in a table, in a mapping, and a graph. So the first thing I do, I'm going to represent it in a table. I'm going to look at my x values, 1, 0, -2, and -3. I'm then going to take those numbers and list them from least to greatest, the x values, and then write my corresponding y values. As I can see, this is a function because the x's don't repeat. I can also take that set and represent it as a graph and draw a vertical line through each point to determine whether it's a function or not. And as you can see, it passes the vertical line test and it is a function. Now when I go to map this set of ordered pairs, I need to take the x values and list them from least to greatest, and the y values and list them from least to greatest. I then go and map the x value to the y value. So -3 goes with 5, -2 goes with 3, 0 goes with 2, and 1 goes to -4. Now I can just look at the x values and see that there's only one ray going off each element, each value, so that this is a function. Now I've taken the same set of data and just changed one number. And I'm going to represent it in a graph, a mapping, and a table again. So the first thing I do to represent it in a table, I look at my x values. And I order them least to greatest and put them in the table, and I include every single one I had. And then I write the corresponding y value. I can easily see that this is not a function because the ones repeat. I can also look at the graph and start drawing a vertical line through each point. And again, I can see that this is not a function because the 1 repeats. I'm looking at the x values. Now when I go to map, again, I must take each number, each x value, list the least to greatest, and I'm only listing it one time. If it repeats, I take the y values and list them least to greatest, and list them one time if they repeat. So, -3 goes with 5, -2 goes with 3, 1 goes with 2, and 1 goes to -4. So now that I've mapped it, I can see that this is not a function because there are two arrows, two rays going off the number 1. That means the number 1 repeats itself and it's not a function. Right, to switch gears here, we've been talking about roster notation. We've been using roster notation to write the domain and the range of a discrete graph. We're going to start writing the domain and range of continuous graphs, so we need to know a new notation called set builder notation. Because with continuous graphs, we're going to be using inequalities because it's going to be a whole range of number. So for instance, if I had a domain that where x was greater than 5, if I wanted to take that inequality and turn it into set builder notation, what I would do is I would start at the end and I'd make a curly bracket, and then I'd go right in front of my x and make a vertical bar. I'd write the letter variable x again, and then I would have my curly bracket. So all I've done to this inequality, x is greater than 5, to put it in set builder notation is, as I've included it in brackets, I put this vertical bar in front of it and I repeated the variable. So this is what it looks like, and this is how we would read it. The curly bracket is read the set of, the variable here is all of whatever variable it is, and the vertical bar is read such that. So we would read this as the set of all x such that x is greater than 5. So that was a domain. Here let's look at a range. using set builder notation. So I've determined my range to be between -5 and 12. So I would write it as -5 is less than y, which is less than or equal to 12. And to take this inequality and write it in set builder notation, I always start at the back here and put my curly bracket. I go to the front and put my vertical bar. In front of that, I put the y, which is the variable we're talking about this time, and then the curly bracket. So this is what it would look like, and how we would read it. Is the set of all y such that -5 is less than or equal to y, which is less than or equal to 12.